Okay, 4.2, as I mentioned before, is really just a continuation of 4.1. It is separated out distinctly differently because of the way the symbols operate, but these are just two more numeration systems, and we're going to learn how to work within them. The first one we're going to look at is called the Babylonian numeration system. I'll show you the symbols in a second, but we'll just read through some of the features of the system. The Babylonian numeration system has repeated symbols for values less than 60. Okay, that doesn't mean we write 60 symbols out, but if we have a number less than 60, we're going to repeat some symbols to get things. If the number is bigger than 60, they use a positional system. Okay, I didn't really go into much detail about positional when we saw that word show before, but our system is a positional system. It means that when we have a single numerator or single numeral in a specific position, it takes on the value of that position, right? So when you have the number 3 in the hundreds place, it means 300s. It doesn't mean 3, right? That's what it means for it to be positional, is that its location within the number matters. A 3 in the hundreds place is different than a 3 in the tens place. Their positional system, however, does not use base 10. It uses base 60. So we have our ones place, we have our tens place, we have our hundreds place, which is 100 or is 10 squared. We have our thousands place, which is 10 cubed. All of theirs are powers of 60. So they have the ones place, the 60s place, the 60s squareds place, the 60s cubes place, and so on. Okay? They do lack the number 0, and you're going to see exactly why that's a problem in one of the examples that I have for you. That is a big problem in their system, actually. All right. So these are our Babylonians. The Babylonians only have 2 symbols. That's something that's kind of friendly. The symbols actually look like an upside-down triangle. They're filled in, but I'll tell you that when I write them out on the screen, I'm going to write them hollow just for the sake of time. But they'll be filled in when you look at them on my math lab. And then the other symbol looks kind of like an arrow or like a less than sign that gets filled in like this. And again, when I write them, I will just write a less than sign for the sake of not having to do all the shading. So these are what they actually look like, or at least pretty close on the left, filled in. My symbols are going to be sort of an abbreviated version of them with a hollow triangle and a less than sign. Okay, everybody good? Okay. Yeah, we'll pause to let you write them down. It's about to get weird. I know. About to get weird. Okay, ready? All right. So, symbols look something like this. I promised you weird. I'm delivering. Okay. Just like before, what I want us to do is to figure out what the symbols are doing. But we're not going to write them individually out because we're going to see a lot of repetition here. We're going to try to group them together. For example, on the first one, we have these 2 symbols here. There's 2 of them, but they're each worth 10. So 2 times 10 would be 20. This is the 20 here, right? And this one right here would be a 1. Okay. The next 2 together would be another 20. And then I'd have a 2. Okay, so far so good? This number is not 20,000 or 21,202. You don't just get to merge the numbers together. That is not what is happening here, okay? But what we do need to notice is that when a number changes from a smaller value into a larger value, it changes position. So we have the ones place, or the 1 symbol, that triangle, followed by a 10 symbol. This changes place value. That's how we identify place value changes. Smaller symbol in front of larger symbol. Okay? Everybody good so far? So these 2 will group together and they will be the number 22. And these 2 will group together and they will be the number 21. That's what we have. But we have them in base 60s. So this is in the ones place. And this is in the 60s place. Okay, just like ours, ones place, tens place, hundreds place. It's ones place, 60s place, 60 squareds place, and so on. So what do? Well, we multiply. We take 21 times 60, and we have 22 times 1. We multiply and we add them together. What does that give me? You're definitely going to want a calculator as you do chapter 4, just FYI. What is it?
1260.
Close. Yeah. Close. 1282. Yeah, 1282. You're going to practice them. That's what you're going to do, and they'll get better. Okay, so this time around, instead of identifying all my numbers first, I'd like for you to look for where you see place value breaks. Anytime you see a place that is smaller in front of one that's larger will be a place value break. Do you see one?
After the 3 ones.
Okay, yeah, after these 3 ones, there will have to be a place value break right here. Yeah, and this one right here after this one. This one has 3 place values. Okay, smaller symbol to larger symbol. For us on this system, it means I have triangle turning into a less than sign, or becoming the less than sign next. Okay, so before the first yellow line I drew, I had 4 10s and 3 1s. How much was that?
42.
That's 43. In between my 2 yellow lines, I have 2 10s and 1 1, 21. And then after my last yellow line, I have 1 10 and 1 1, 11. We always start on the right-hand side. It's the 1s place, the 60s place, and then 60 squared. And by the way, 60 squared would be 3,600. You can square that, right? Just put your calculator if you don't want to do it in your head. 60 squared. So what I do is I take the number that's in that place, 43, and I multiply it by the place value. So I have 43 times 3,600, or you could write 60 squared, plus 21 times 60, plus, and I have 11 times 1. And then it's a calculator exercise, right? Absolutely. So put those pieces into your calculator, add them together, all the things. What do you get? Yep, 156,071. You might be thinking about right now, this is why the Babylonians are no longer around. Maybe. This is rough, isn't it? It is. This is rough. Okay. But it's harder going the other way. I know. All right, so let's take a look. I know. 3,280. Okay. So notice, what operations did we use to get this to work? Multiplication and addition, right? It was multiplication and addition to turn their number into our number. So if I'm going to reverse the process, what do you think I'm going to do in terms of operations? Division, subtraction. So I'm definitely going to see some division going on. The subtraction occurs within the division, so yeah. All right, so what does that mean? Well, let's actually write this down first. We have the 1s place. We have, actually I'm going to write it the other direction. All right, we have the 1s place, and we had the 60s place. We had 60 squared, which was 3,600. 60 cubed. What is 60 cubed? That's what I was thinking. 216,000. I'm not going to write the comma between them because I want to make sure you see the commas separating my individual pieces. All right, so that's big enough for us. These are their first four place values. Okay? So what you're going to do is you're going to look at which of those numbers will divide into the number we're given, 3280. Which is the biggest number that will divide into 3280? 60, right? That's the biggest one. 3600 is just slightly too big. So what we're going to do is we're going to do a division algorithm. It's going to look a little bit like division with a couple differences. So we're going to do a 60 on the outside, and we're going to do our 3280, but it's almost going to look like I have another division like mirroring on the other side. Okay? Your calculator is going to be your best friend. Like, you really need it for this. You're not going to do this in your head. This is not going to work. So I need to know how many whole times 60 goes into 3280. 54. So the 54 will go here, and then we will multiply. What is 54 times 60? 3240. And we will subtract. So there's that subtraction going on. And if I subtract that, what do I get? I have 40. And then I work my way down. I already did the 60. Now I'm going to do the 1. Okay? Now I know it feels a little bit funny because you're like, well, division by 1 is really not exciting. It's okay. It can be not exciting. 1 goes on the outside. How many times does 1 go into 40? 40 times. 40 times 1 is 40, and when we subtract, we get 0. These numbers on the right-hand side, the 54 and the 40, are what tell us what symbols to draw. I need to draw the symbols that represent the number 54, and then I need to draw the symbols that represent the number 40. So, how do I get 54? Well, to get 54, I need 5 tens, and I need 4 ones. And they may do some stacking in this as well. So you might see them do it, I think, in fact, you'll see something that look more like this. I'll do it too for some space, because otherwise I'm going to run out of space on my screen. 54. And then I need the number 40. How do I get the number 40? 4 tens. And that's it. Fun. The number just got bigger for part 2, right? It did. 43,206. What is the biggest number in my list on the top that will divide that one? 3,600. So we will start with 3,600. So 3,600 into 43,205. And your calculator is going to do it for you. It's going to tell you how many whole times it goes in. How many whole times does 3,600 go into 43,000? 12. And what is 12 times 3,600? 200 even? Okay. Subtract, and I get 5. I'm about to do something that's going to feel a little bit weird, and it really isn't super critically necessary right now, but we're going to need it when we get into the later part of chapter 4 anyway, so I'm going to model it now anyway, okay? We always go down in place value. So we did the 3,600, now we're going to do the 60. And 60 is not going to go into 5, so it's going to create a 0 over there. It's not going to be a very exciting step, but I need it represented later. So we're going to do it right now anyway. And the last thing I will divide by is the number 1. So how many times does 1 go into 5? 5 times. 5 times 1 is 5. Yeah, the remainder is 0. Okay, so far so good? All right. How do I get the number 12? A 10 and 2 ones to make the 2. And I don't have a symbol for 0. So we're just going to keep going. How do I get a 5? 5 ones. This is correct. My math lab might have a space in between them like that, or a little bit of 1. But this is a problem. If I started with this, because of the stacking, or potentially because of the space, you might at least recognize that there's a place value difference, right? But you probably would think that this 5 triangles were in the ones place, and this 12 was in the 60s place. That's a problem, right? Truly, that would be a problem if you were doing some kind of bookkeeping back in the Babylonian days. Yeah. So it's not going to be a problem as you do your work, but I just want to point out to you that there is a flaw in the way that the system is created because I don't have a 0. I have a problem. Okay? All right, our last system, Mayans. The Mayans have a 0. That's good. They got other issues, but they got a 0. It is written vertically like our Chinese friends. They have dots and lines. So let me actually tell you the symbols because it'll make more sense with the way that this is described below. The number 1 is a dot. The number 5 is a horizontal line, short line. The number 0, it looks like this. What is it with zeros looking complicated? I don't know. It's not always looking like this either. Again, the other book that I teach out of it doesn't look like this. It's got the same shape. They call this a clam shell. That's what they're calling it. All right, so back to the descriptions. The dots are written on top of the lines within the place value. So we have dots on top of lines. This one is a modified base 20 system. We're going to talk about why. But they have the ones place, and then they have the 20s place, and then they have a place value that's 20 times 18. That's a little weird. Again, we'll talk about why. And then the powers of 20 start. 20 squared times 18, 20 cubed times 18, 20 to the 4th times 18 after that. And they repeat the symbols within the position like the Babylonians did. Okay. Why do you think they might have used a base 20 system? Why do we use base 10 system? What's your guess? Nope.
Because we have 9 individual numbers.
But you got it. It's fingers. How many fingers do you have?
20 fingers?
10. No, they did not have 20
They had
fingers in
toes.
Babylonian or in the Mayans. No, but they had fingers and toes, right? And they did not have shoes that covered up their toes like many of you do today, right? So fingers and toes. My brother thinks this is really funny. He says, I should tell all my students you should be counting on your fingers and toes. I don't know, whatever. So he's weird. All right, so Babylonians use that. Why do they do it modified? What is 20 times 18? 360. Can you think of something in our world that's approximately 360? Days in a year. And do you remember what the Mayans are famous for? The calendar. Days in a year. That was something that they were very preoccupied with, right? So they wanted their place value system to represent sort of their, perception of the world. This 360 was an important number for them. So that's why it's happening. It's not terribly awful to use. So here's what we're going to do. I'm going to do these two with you, 5 and 6. That will end our class. I'm going to pause the video, let y'all leave. I'm going to do 7 and 8. So when I post it, it's going to have the whole thing there, and you can go back and you can watch the last, it'll be probably 5 to 7 minutes of the video, and you'll be able to finish it up, okay? So dots and lines, that's what we get, and we get these shell things or these clam shell things showing up every now and then. Okay, so place values separate just like they did with the Babylonians. If I have dots above lines, that's a place value. So this is one place value, and when it changes from a line to a dot, it changes the place system. So on the first one, there are 2 numbers or 2 place values, okay? Dots are worth 1, lines are worth 5. So if I have 4 dots and a line, how much is that worth? That is worth 9. And if I have 4 dots and 2 lines, how much is it worth?
14.
It is worth 14. The number is not 914. Okay, just like with the Babylonians. their place value system comes into play. So this 9 is in the 20s place, and the 14 is in the 1s place. So I have 9 times 20 plus 14, or 14 times 1. What does that give me? 194. I know, at this point your brains are on overload. It's okay. We're almost done for today, I promise. You got the whole weekend to parse through the pieces of this one at a time. All right, next one. So clam shells, they actually take up a whole place value. Okay, so he's all by himself being the number 0. I have dots and lines that are grouped together above him. I have 2 dots and I have 3 lines. What is that? 17. Lines are worth 5, dots are worth 1. Underneath my clam shell, I have a line, and then I have a dot, and then I have another line. Okay, that's not, those are not all together in one system. I mean, that one's place value, right? I can't go from lines to dots without changing place value. So this one right here, that line is its own place value of 5. And then my dot in my line below would give me 6. Okay, so 6 is in the 1's place, and the 5 is in the 20's place. What's the next place value? 20 times 18. So I'll write it as 20 times 18. We've already talked about that being the number 360. And then the 17 is in the 20 squared times 18. Okay? 20 squared times 18 is 7,200, just so you know. So we're going to take 17 times 7,200 plus 0 times 360. That's super exciting. I have 5 times 20, and then plus the 6, or 6 times 1. The calculator figures it all out for you. What do you have? You don't have a calculator. All right, it's 122,506. At least that's what my notes say. Did anybody get that? I got a thumbs up. Okay. Now, I'm going to do the next 2 slides, or the next little bit here. In fact, you know what? I'm going to stop the video. I'll record the second one later because I actually have to head to a meeting right now. So when you get back in there, you're just going to look for section 4.2, part 2. And that's where it'll be.